Section 10.2 is plane curves and parametric equations. Now what we're going to do in this section is we're going to talk about a new concept that's going to allow us to use functions to study curves that when you graph these curves in the xy plane, they neither represent y as a function of x nor x as a function of y. So what we're used to seeing are things like this: y equal f of x, where x is the independent variable and y is the dependent variable. Again, things like y equals x squared plus 5. Again, x is your independent variable, y is your dependent variable. And that's a function, that's what we're used to seeing. But if we were to try to talk about this curve, notice that this curve here is neither a curve that's a function of y nor a function of x. So to talk about a curve like this, we use what's known as parametric equations. Parametric equations can represent a curve like this in the xy plane, where what we do is we let x equal f of t, some function of t, and y equal g of t, some function of t, and that makes t, or that parameter, the independent variable, and then x and y become the dependent variable. So we make functions that represent all the x coordinates of this curve, and a function that represents all the y coordinates of that curve, and then all of a sudden something that wasn't a function we can rewrite as a function with this system of equations. Now the orientation or the direction of the curve when you're dealing with parametric equations is always determined by increasing values of t. We always determine the orientation by increasing values of t. So the way that we graphed this before, this would have been the orientation because in the way that I drew it, that would be the increasing value of t. Now let's work with some parametric equations. We want to sketch the curve represented by the parametric equations and indicate the orientation of the curve, and then write the corresponding rectangular equation by eliminating the parameter. The first part is just asking us to sketch the curve. So we want to sketch this guy right here. Well, in algebra, when we learned to sketch things for the first time, what we did was make a table of values. So that's how we're going to learn to sketch these parametric equations. What we're going to be plugging into is the variable t. So we're going to choose something that's a little bit negative and a little bit positive so that we have a full range of what's going on here. We're going to say, well, let's let t equal -3, -2, -1, 0, 1, 2, and 3. And we're going to plug that into each one of these equations so that we can figure out what is the x value, what is the y value, and then each one of those x's and y's is going to represent an ordered pair. When t is -3, I'd have -3 squared minus 3, that's 9 minus 3, or that'll be 6. When t is -2, -2 squared minus 3, 4 minus 3 is 1. When t is -1, -1 squared minus 3 would be -2. When t is 0, 0 minus 3, -3. When t is 1, 1 squared minus 3, -2. When t is 2, 2 squared minus 3 is 1. And finally, when t is 3, 3 squared minus 3 is 6. Now let's put in all the y's. So when t is -3, we'd have 2 times -3 minus 1. -6 minus 1 is -7. -2, 2 times -2 minus 1 is -5. -1, 2 times -1 minus 1, -3. 0, 2 times 0 minus 1, -1. A 1, 2 times 1 minus 1 is a 1. 2, 2 times 2 minus 1 is 3. And then finally a 3, 2 times 3 minus 1 is 5. Now each one of these represents an ordered pair. So we're going to graph each one of these ordered pairs on this coordinate plane. So here's your x-axis and here's your y-axis. And just so that we label it's a little easier, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Then I'm going to label a little bit of the negative here as well, so it's easier to graph these points. The first ordered pair is the point 6, -7. So 6, -7 would be right there. Then 1, -5, 1, -5 here. -2, -3, -3, -1, -2, 1, 1, 3, and then 6, 5. Now to graph this, you want to connect the dots in the order in which you graph them. So we're going to go just in the order in which we graph these dots. And that also is going to tell you the orientation of the curve. Since we started from the bottom here and went up and towards the right, that's going to be the orientation of our curve. This is the curve that's represented by these parametric equations. So sketch the curve and indicate the orientation. We've done both of those. Now what we want to do is write the corresponding rectangular equation by eliminating the parameter t. Well, how do we do that? Well, when we have these types of parametric equations where the x and the y are equal to just something that's a polynomial or something that isn't trig, we're going to follow these directions in order to write the rectangular equation. So the first thing we want to do is solve one of the equations given there for t. We have two options. We have x is equal to t squared minus 3, and we have y is equal to 2t minus 1. And we have to solve one of these for t. Well, we are going to choose this one here, and the reason we won't choose the x one is because if we were to try to solve for t here, we'd have to take the square root, which means we'd have two separate equations because of the plus or minus. So anytime you have t raised to an even power, you're going to avoid using that particular equation because you'd end up with two separate equations. So always use one where your t is either raised to an odd power or something that you can solve explicitly for the variable. So if I solve 2t minus 1 for t, I'd first add 1 to both sides, and then divide by 2, and I'd have y plus 1 over 2 is equal to t. So the first step is to solve for t in one of the equations. Then you're going to substitute that into the second equation. So remember, the second equation is this one that I crossed out here. It's that x equals t squared minus 3. So what we're going to do is instead of writing t in this equation, we're going to replace it with what t is equal to, which is y plus 1 over 2. So we end up with x is equal to y plus 1 over 2, quantity squared, and then still minus 3. So all we did was replace the t with what t is equal to. If I clean this up a little bit, I could distribute the square to the numerator and the denominator of this fraction, and that would be y plus 1 squared all over, well, 2 squared is 4. Well, if you look at this equation, this is a parabola that opens to the right, which makes sense because that's what we drew there, a parabola that opens to the right. The last and final step is to interpret the results and watch the domain. So here, if you look at the picture, the graph, the domain would be all x's greater than or equal to negative 3 because that's the furthest we go to the left. So our domain here, we would say would equal x is such that x is greater than or equal to negative 3. Now in WebAssign, it's going to have the domain already written for you, so you won't have to put that in there when you're doing these problems. Also, let me show you how to put this in a calculator. In a calculator, if you were wanting to graph parametric equations, what you're going to have to do is change the mode of your calculator. You're going to want to go from function mode to parametric mode. So scroll down, choose parametric, and hit enter. Now we're going to go to the y equals button, and we're going to plug in this particular parametric equation. Remember, it was t squared minus 3. The t button is the same as the x, so you use that button. So t squared minus 3, that's what it was for your x. And remember, for your y, it was 2t minus 1. Now, before we hit graph, I'm going to change the format of this. So if you hit window, notice that it tells you that your minimum t value is going to be 0. We don't want our minimum t value to be 0, so let's go ahead and just change that to negative 10, just so that we have a better picture of our graph. Now hit graph, and notice that this graph here looks very much like our graph. Let's look at number 2. Number 2 has the same directions. We want to sketch the curve, indicate the orientation, and then write the corresponding rectangular equation by eliminating the parameter. Notice that number 2 is trigonometric. It's x equals 2 cosine of t and y equals 3 sine of t. Because we're looking at something that's trigonometric, when we're choosing our t values that we're going to plug in, we're going to plug in radian measures. So we're going to plug in things like 0, and then maybe pi over 4, then pi over 2, 3 pi over 4, pi, 5 pi over 4, 3 pi over 2, and then let's just go all the way to 2 pi. So we're just plugging in some radian measure, not every single angle between 0 and 2 pi, but enough so that we could graph this particular parametric equation. And then you're plugging the t's in to solve for your x and your y. So when t is equal to 0, we have 2 times the cosine of 0, which is 2. Plugging in a pi over 4, 2 times the cosine of pi over 4 becomes square roots of 2. A pi over 2 would give us 0. A 3 pi over 4 would be negative square roots of 2. Pi, negative 2. 5 pi over 4, also negative square roots of 2. 3 pi over 2 is 0, and at 2 pi, we'd be back at 2. Now let's plug things in and get the y values. 3 sine of 0 would be 0. 3 sine of pi over 4 would be 3 square roots of 2 all over 2. 3 sine of pi over 2 is 3. 3 sine of 3 pi over 4 is also 3 square roots of 2 over 2. Pi would be 0. 5 pi over 4 is negative 3 square roots of 2 all over 2. 3 pi over 2 is negative 3, and 2 pi is 0. So now we're going to have to graph this. Notice that we have the square root of 2 and 3 square roots of 2 over 2. Let's figure out what those numbers are real quick on a calculator so we can graph this a little easier. The square root of 2 is approximately 1.4, so we're going to use 1.4 when we're graphing the square root of 2. And then 3 square roots of 2 divided by 2, it's approximately 2.1, so we're going to use 2.1 when we're graphing 3 square roots of 2 over 2. And since we have something with decimal values, what I'm going to do is I'm going to make each one of these little tick marks here be half a unit. So this is going to be where 1 is, 2 is, and 3 is, just so that it's easier to graph this in the end. So let's graph the first ordered pair. The point 2, 0, 2, 0 is right here. Then the square root of 2, 3 root 2 over 2, that's going to be a 1.4 comma 2.1. So 1.4 is about here, and then 2.1 would be right there. And then 0, 3, and that's going to be a negative 1.4 and about 2.1, so negative 1.4 and about 2.1 is about there. And then we'd have negative 2, 0, and then a negative 1.4, negative 2.1, so negative 1.4, negative 2.1 is going to be about here, and then 0, negative 3, and the last one's right back at 2, 0. So graph the points in the order in which you drew them, and then give this curve some orientation. And again, that's just going to be in the order in which you drew. So we've sketched the curve and given the orientation. Now what we want to do is write the rectangular equation, so we want to eliminate the parameter t. Well, in the last ones, what I said was you wanted to solve one of these for t. You don't do that with trig. If you have trig, what you're going to do is use a Pythagorean identity to eliminate the parameter. So what Pythagorean identity can we use if we have 2 cosine of t and 3 sine of t? Well, the Pythagorean identity, that is cosine squared theta plus sine squared theta equals 1, because it relates cosine and sine. I don't have thetas, I have t's, but theta is just a dummy variable, so we can think of this as cosine squared t plus sine squared t equals 1. And this we can rewrite as cosine of t quantity squared and sine of t quantity squared. Well, now we have enough information to get this out of t's and into x and y. Well, how? Well, I know that x is equal to 2 cosine of t, and that y is equal to 3 sine of t. So if I can just get cosine of t all by itself, I can then replace it in this Pythagorean identity. If I divide by 2, I get x over 2 equals cosine of t. And here, if I can get sine of t all by itself, then I can replace it in the Pythagorean identity. If I divide by 3, I'd get y over 3 is equal to the sine of t. Therefore, instead of writing cosine of t, I can write x over 2, that gets squared, plus, and again, instead of writing sine of t, I can write y over 3, and that still gets squared, and it's equal to 1. Distributing the square, I would get x squared over 4 plus y squared over 9 is equal to 1. Now we can look to find the domain of this from the picture as well. WebAssign not going to ask you for the domain of this one, but if you look here, well, you can tell that your x's are trapped between -2 and +2. So we can say that the domain here is our x is such that -2 is less than or equal to x, which is less than or equal to 2. The last thing that we're going to do in this section is learn how to find a set of parametric equations if we're given the rectangular equations. Now, when you're finding a set of parametric equations, the problem is that these, especially for something linear, like we're looking at here, they're not unique. So you and the person next to you could have two separate answers and they're both correct. So I'm going to give you a general guideline to do this problem. What we're going to want to do is let one of the variables equal t, and usually you choose the independent variable. So here notice that x is your independent variable. So we're going to say, okay, let x equal t. Well, if x is equal to t, just plugging straight in here, you get y is equal to 3t plus 1. Now, does that work? Because we are given some initial conditions. It says that needs to satisfy that given condition. What's the given condition? Well, when t is 1, you end up at the point -2, 5. So does that work for this? Well, let's see. At t equal 1, what would x equal? 1. Well, is that right? No. So that means that this cannot be the parametric equations that I need. So instead of letting x equal t like we did here, since when t is 1, we need to be at x equal -2, let's let x equal -2t. Well, if x is equal to -2t, again plugging in the x for here, we'd have y equal 3 times -2t plus 1, or y equals -6t plus 1. Well, does this work? Let's check. What happens when t is equal to 1? Well, I'd have -2 times 1, which is -2 for x. So far, that's perfect. What about for y? Well, at t equal 1, I'd have, for my y here, -6 times 1, which is -6 plus 1, which is -5. Perfect, that's what I need. Therefore, a set of parametric equations entered in as comma separated list would be x equals -2t, comma, y equals -6t plus 1. We are done with this problem, so let me just recap. Typically what I tell students to do is start by letting the independent variable equal to t and make sure it matches that given condition. If it doesn't, then think, okay, well, what could I let it equal so it does equal, in this case, -2, or if it were a different number, that number. Now, I also again caution, because these things are not unique. So this is done and this is what you would enter in. But I just want to show you how it's not unique. We could have just as easily said that we wanted x to equal, instead of this, -2t, t minus 3. Because what happens at t equals 1? Well, x would equal 1 minus 3, which is -2. That's perfect. That's what we would need. And then y would equal 3 times t minus 3 plus 1, again plugging into this guy, and that when we distribute would be 3t minus 9 plus 1 is going to be -8. So what happens at t equals 1? Well, I'd have y equals 3 times 1 minus 8, which is -5. Again, that's perfect. So this could be our answer, or our answer could be x equals t minus 3, comma, y equals 3t minus 8. Both are correct. So be careful with parametric equations because they're not unique, especially when you're looking at something that's rectangular like this, that's linear, or sometimes even when it's quadratic. Just make sure that whatever you choose ends up working for your given conditions. That's it for plane curves and parametric equations.